In this video, I want to talk about combinational logic design using System Verilog. So the first concept that I want to go over is with the concept of bitwise operators. So let's just create a module that can do some bitwise operations for us. So as I said before, we need to specify the module by module and end module. And then we have to give it a name. So here I just gave it this generic name. I called it gates. Inside parentheses, we have to list the set of inputs and outputs that we have for the module. So we have input as the keyword, logic again as another keyword that it says to System Verilog that the sets of inputs are logic values, so true or false. And then something that you haven't seen before, this square bracket with 3:0 inside. So this basically specifies that the inputs that we have here, A and B, are not only 1 bit, but in fact they are 4 bits. So if you remember before, there was another way of showing 4-bit values by using subscript. So this basically means that input A is actually A3, A2, A1, and A0. And similarly for B as well. So input B is B3, B2, B1, and B0. So by specifying the size or the bit numbers here, we actually tell System Verilog that A and B are 4-bit values. As for specifying the outputs, we have the keyword output, then logic. Output specifies that the now we are trying to define the sets of outputs of our module. Logic specifies that the outputs are logic values, and then we have, similarly as we did with the inputs, the outputs are all 4-bit values too. Inside the module we have 2 lines of comments. If you remember from before, if we wanted to have a single line comment, we could have used 2 slashes. If we want to have a multi-line comment, we can put our comment between slash star and then star slash, and then whatever between these two is written is considered as comment and won't be executed. So now for this function, I want to create 5 different functionalities. I want y1 to be the AND of A and B. I want y2 to be the OR of A and B. So these 2 symbols you already have seen before. I want y3 to be the XOR of A and B. So this is the new symbol. So it is either called the caret or the exponent, right? So this is to signify that the operation is XOR. So this is the symbol for XOR operator. I want y4 to be the NAND of A and B, and I want y5 to be NOR of A and B. So as you can see, I'm using this assign keyword for all of them because that's what I'm actually going to do. I calculate the right hand side and I assign the value to the variable on the left. But one thing that you should notice is that before, whenever we did AND or XOR or any type of gate, we were actually applying them on individual bits, not on values that have more than 1 bit. So when we specify it this way, the System Verilog knows that it has to do the calculations bit by bit. So let's say we have A to be 1011, and let's just say B is 0100. So based on this, y1, as I said, is the result of calculating the bitwise AND of A and B. So that means that we have to calculate the AND of 1 and 0, and that is going to be 0. So this is the result of y1, basically the least significant bit of y1. Then we do it for the next 2 bits. Again 0, then the next 2 bits 0, then the next 2 bits 0. So y1 is going to be 0 if we provide a and b as inputs like this. Similarly, you can do it for y2 as well. Again, you calculate the bitwise operation between the bits of a and b. So if I do that, y2 is going to be y1 1 1 1. y3 is the result of XORing. So you remember XOR of 1 and 0 or 0 or 1 would be 1, right? So y3 is also 1 1 1 1. And then you can do the same for NAND NOR as well. When we do the synthesis, one thing that you notice here is that the fact that A and B are 4-bit values is specified in the synthesized circuit too. Of course, in reality what we will have is that we have 4 copies of this circuit, right? Each one only using basically single input AND gates, right? But here, to make things concise, we just say that all the inputs and outputs here are having 4 bits. So as you can see, y3 was XOR, so we have A and B being connected to the 2 inputs of this XOR gate, so this creates y3. y1 was AND, so we have here as the result of y1. y4 was NAND, so we have this additional NAND gate that creates y4. y1 is mentioned here as one of the outputs, and then we have y2 as OR here and y5 as NOR. So this is one type of operation that we can have using system Verilog when we are working with combinational logic circuits. So what if we want to apply a function on all the bits of one single multi-bit number? So here is an example. Here I want to create a module that calculates the result of ANDing all the bits of an 8-bit number. So again, we have module, N module. The name here, we just assign it as AND8. And remember, the names cannot start with a number. So we have input logic inside square bracket 7:0. So that means that the input A is basically having 8 bits. So A7, A6, A5, A4, A3, A2, A1, and A0. So this is the value for A. But the output here is only 1 bit. And the reason that it is 1 bit is that we haven't specified this value at all. So when we say assign y equals AND sign A, so remember this one was basically the AND operator. So that tells system Verilog that we want to AND all the individual bits of variable A and create a value and then assign it to y. So this is an alternative way of writing this operation instead of ANDing all the bits individually in this format, right? Because this one, we can do that too. We can say assign y equals A in a square bracket 7. That means that take out the 8-bit of variable A. And then AND it with A6, basically the 7th bit. And then AND it with A5, basically the 6th bit, right? And then do that all the way to A0 or the 1st bit, right? But instead of doing that, we can just simply write y equals AND operator and then A. If we do the synthesis, this is the synthesized circuit. We have A to be an 8-bit value, and then all the individual bits are separated and then fed to an 8-bit 8 input AND gate, and then value Y is being created. What about conditional assignment? And that is very useful when you want to define multiplexers, right? So in multiplexers, if you remember, we had a set of select inputs and we had a set of regular inputs. So based on the values of the select or control input, we chose one of the inputs to be delivered to the output. So let's just create a 2-to-1 multiplexer here. We have module and module again. The name of the module, we call it mux2. And as for the inputs, we have input logic 3:0, D0 and D1. So we have these two inputs, each having 4 bits. So basically this is a 2-to-1 multiplexer that selects between two 4-bit inputs, right? Not necessarily 1-bit input, but 4-bit inputs. We also have another input which is only 1 bit. So that's why we separated that from the regular inputs that we have. So we want to select between any of these 4 bits input by using this 1-bit select signal. So we again mention input, logic, and then S. Since the size is only 1 bit, we don't specify it at all. And then for the output logic, again it's going to be 4 bits. So now to do this conditional assignment, if you have taken any programming languages before, you are probably familiar with the ternary operator. A ternary operator is an operator that has 3 inputs, right? So for example, an AND or is a binary operator because it only has 1 input, right? A ternary operator, like the conditional operator that we have here, has 3 inputs. So let's just see how it works. So we again have the keyword assign, and then we say y equals s question mark d1 colon d0. So the way that you should interpret this ternary operator, basically, which is a combination of a question mark and a colon, is that you just assign a value to y given the value of s. So what does it say? It says y equals s question mark d1 colon d0. So that means that if s equals 1, so let me just write it down. If s equals 1, or if s is true, then y is d1. If s equals 0, y equals d0. And that's the basic functionality that we want for the multiplexer, right? So if you remember, for the multiplexer, if the select signal was 0, the first input was selected. If the selecting signal was 1, the second input was selected. So this is basically what we have here. We say y equals s question mark d1 colon d0. So if s is 1, the first input is selected. If s is 0, the second input is selected. And as for the synthesis, this is basically the synthesized circuit. You're familiar with the trapezoid shape that we use for multiplexers, right? So this is in fact a 2-to-1 multiplexer. We use the select signal to select between either D0 or D1 to be delivered as the output. Another concept that is important in combinational logic design is the concept of internal variables. Because whenever you have functions that are very complex, you may need to have some internal variables that are being used to store the intermediate values uh, for calculating the final result, right? So you don't have to always specify those in the list of inputs and outputs. They are only defined within the module. So here we have an example of a full adder. Basically, a full adder is a unit that is being used as a building block of creating um, an adder circuit. This is something that I'm gonna go over at later lectures. So basically, when you add two multi-bit numbers, so let's say we want to add two 4-bit numbers. So what you basically have for each calculation, you can say you add this bit with this one, right? And then you have a carry in from the previous stage also. So you have C in, this one is, let's say, bit A, this one is bit B, and then what you basically have is a summation, the result of the summation, and also possibly a carry out to the next addition, right? So a full adder is basically one single unit that does this calculation for us. So let me just erase this so it doesn't look like a T. So I just put the plus sign here. So as you can see, the sets of inputs for this module are A, B, and carry in from the previous stage, and the set of outputs are S and out, and all of these are single bits. But to do the calculation, we may need to have some internal nodes or internal variables as well. So what we do is that inside the module, we define these two internal variables. So we just say logic P and Q. So this specifies that P and Q are logic values, so they're either 0 or 1, and their size is only 1 bit. And then we say assign P to be XOR of A and B, so P is A XOR B. Remember, this one is the exponent or the caret sign, which is used for representing the XOR. And G, it is the AND of A and B, so this is basically AB. And then we use these internal variables to do the rest of the calculations and find out the values for S and C out. Of course, for this example, this is very simple. You could have done it without defining these internal nodes as well, because the function itself is not that complicated, right? But still, it's a good example for you to see. You don't necessarily always have to work with the sets of inputs and outputs. You can have some internal variables defined too that are only defined inside the module. So you don't have access to them from the outside of the module because they are not listed as either the input or the output of the module. And this is the result of synthesis of this module. So now that we have seen several operators and several functionalities for combinational logic circuit, it's a good idea to go over the order of execution of operators. Because if you have a script or a module and inside of it you have some logic assignments, how can you be sure that the function that you plan to execute is executed correctly? Because depending on the way that you write the function, some of the operations may have a preference or may have a higher order of execution in System Verilog. So the order is like this. So the first or the highest order is given to the not operator. So anywhere you have, let's say, tilde A plus B, right? Or B. So this basically is A bar or B, right? But between this operator and this one, first the tilde or the not operator is being executed. So it is not going to be A or B bar. It's going to be A bar or B. After that, we have multiplication, division, and modulus. Then we have addition and subtraction. Then we have shift, whether shift to the left, shift to the right. Then we have arithmetic shift. Again, arithmetic shift to the left, arithmetic shift to the right. We will go over them at a later lecture. Then we have comparisons. Then equal or not equal. And then and, NAND, XOR, XNOR, OR, NOR, and finally the ternary operator. So whenever you want to define a function, you should keep that in mind, that the order of the operators is not all the same, right? So not necessarily when you have an operator appear earlier, that means that it's going to be executed first, right? So this is something that you should always keep in mind. So now let's just see how we can represent numbers in System Verilog. So the general format for representing a number in System Verilog is like this. So we have the capital N, which is there to show the number of bits that you have for your number. Then you have single quote as a separator. You have this capital B, which specifies the base. So you can have a B as binary, D as decimal, O as octal, and H as hexadecimal, right? So if you don't specify, the default is going to be decimal. And then this whole thing is also optional, right? So you don't have to always specify it, but it is recommended that you do. So let's just go over some examples of representing numbers in System Verilog. So for the first example, we have 3 single quote B101. So this 3 specifies that our number is having 3 bits. This B specifies that the number is in binary. So 101 is going to be represented or interpreted as a binary number with the decimal equivalent of 5. So this is what is it going to be stored, 101. But what if we have no number specifying the number of bits, but single quote B11? So in this case, the size is not specified. So the System Verilog uses the default size. So let's say if it's the default is 32 bits, it considers that as a 32-bit number. But since it is specified as a binary, this will be interpreted as a binary number. So its value is going to be 3. But the value that is going to be stored is 000 all the way to the last 2 bits, which are 11. So this is basically the default size that it is using. So 32 bits or 64 bits. What about this one? We have 8 single quote B11. So that tells System Verilog that the number of bits is 8. The number is binary, but we only specify 2 values. So it knows that the rest are going to be 0. What about 8 single quote B101 underscore 1011? So it tells System Verilog that the number is 8-bit, it is binary, and its value is 101 1011. So this underscore is there to basically ease up the reading. It doesn't have any implication in terms of the actual number. What about this one? 3 single quote D6. We say that this is a 3-digit number, and it is a decimal number. So the decimal equivalent is going to be 6, right? But the value that is going to be stored is 110. Again, it stores the values as binary numbers. This one is 6 single quote O42. So O means that it is an octal number or base 8. So 42 is interpreted as a number in base 8, which is equivalent to 34 in decimal. And since we specified it to have 6 bits, it's going to be stored as 100010. What about this one? 8 single quote HAB. H is for hexadecimal numbers. So we have an 8-bit number with values being A and B. You remember A was 10, B was 11, right? So the decimal equivalent is 171, and the value that it is stored is like this: 1010101011. And then finally, if we don't specify at all, let's just say we just simply put 42. It is an unsigned decimal number, so the default is decimal. The size, it is going to use the default size of the system, whether it is like 32-bit or 64-bit, and its decimal equivalent is 42, right? Because it is assumed as decimal number. And it stores the binary equivalent using the default size of the numbers. So now that we have seen this, let's just go over some more examples using system Verilog. So the first example is bit manipulation. So let's say we have some binary numbers that we want to combine them and define them as one single variable. So let's say we have variable A that has 3 bits, so A2, A1, and A0. Then we have a variable B which we want to repeat B0 3 times, so B0, B0, B0. And then we want to repeat A0 one more time, and then finally at the end we want to put these 6 bits at the end of it as a 6-bit binary number. So the way that we can achieve that is by using curly braces. So curly braces is basically used to concatenate binary numbers into a single binary number. So executing this, we have A2, A1. I'm sorry, I made a mistake. This one is only 2 bits because it has only A2 and A1. It doesn't have A0. A0 is here. So Y is going to be A2, A1, and then 3 copies of B0, because you see we have 3, and inside of these curly braces we have B0, so that means that repeat this 3 times, and again this one is inside of curly braces. So we repeat B0 3 times, and then we have A0, and at the end we have 1 0 0 0 1 0. So this is how we can create a 12-bit signal by using this above statement. So as you can see, these numbers, they may mean different things. So this can be only a single number. These A and B can be the outputs or inputs of a system, right? But you can combine all of them into a single variable. So this is something that usually happens, that not every binary number that you see has similar definitions for every single bit, right? They may have different definitions for the individual bits. But one thing that you need to consider is that the underscore, when we use it for defining the numbers, is only used for formatting and system verilog ignores underscores. So let's take a look at another example. So this one is an example of structural modeling. Basically, we want to use the 2-to-1 multiplexer that we had before, the one that used that was designed to choose between two inputs each having 4 bits, and we want to combine them to create a 2-to-1 multiplexer, but now this time it is choosing between two variables that have 8 bits. So we have module and module again. The name of the module is max2 underscore 8, right? So since this underscore is part of the name, it's not going to be ignored. It is going to be ignored when it is used for formatting a number. As for the inputs, we have input logic D0 and D1, each having 8 bits from 7 to 0, the number of the bits. We have the input logic S, which is only 1 bit, and then we have the output logic Y, which also has 8 bits. So now what I want to do is that I want to create two instances of the 2-to-1 multiplexer that we had before. One for calculating the or selecting between the lower half of the two 8-bit numbers, and one for selecting the upper half. So I just say max2, and then I call this instance LSB max, or least significant bits max. And for the input, I just give the lowest bits of the number. So this is basically D03, D02, D01, and D00, and this one is D1 subscript 3, D1 subscript 2, D1 subscript 1, and D1 subscript 0. So this part basically selects between the least significant half of the two numbers, and then assign it to the least significant half of output Y. So it is going to be Y3, Y2, Y1, and Y0. And then the next one is another instance of max2, but this one is called MSB max, or most significant bits max. And we use the most significant half of the two inputs, D0 and D1, plus the single bit select input, and then we assign it to Y7 to Y6, Y5, and Y4. And when you do the synthesis, this is basically what it looks like. So this is a way of reusing basically the module that we have defined before to come up with a module that can accept 8 inputs. So that brings another question. So isn't there a better way of doing that? So what if we have a module, a single module, but we can have a parameter that selects or specifies the number of inputs? That's one way of doing that too. So here you see the same 2-to-1 multiplexer, but this time we have a parameter that specifies the width of the multiplexer. So to specify the parameter, right after the name, you just put a hashtag or the number sign. Inside the parameter parentheses, you have parameter space width equals 8. So this parameter is a keyword, and this width is the name that we are giving this parameter. So we basically define a new parameter with the name width, and we just equal it to 8 as the default value. And then we write the rest of the function based on this new parameter. So for the inputs, we have input logic, and we have width minus 1 colon 0. So this, when width is 8, is going to be 7 colon 0. And that would be the size of the input variables. For the select signal, it's going to be only 1 bit, so we'll leave it at that. And again, for the output, we have the size of the output to be width minus 1 colon 0. So that means that this is again going to be 7 colon 0. And then we just simply assign the output y using the ternary operator. So if s is 1, d1 is going to be assigned to y. If s is 0, d0 is going to be assigned to y. But now let's say we want to create, or we want to call this module in another module. What we can do is that we can just say mux2. This creates an instance of this new version of mux2, and then we, since we didn't specify the width or the parameter, it uses the default value, which is 8 bits. However, if you want to call this module with a different width, what you can do is that you can specify the size or the width by hashtag in parentheses 12. So when you do that, it basically creates an instance of this multiplexer, but now with the width parameter to be 12. So this is an example of creating parameterized modules. So now let's just talk about the floating output, because this was something that we have seen before too, that for logic variables, one possibility was that the output is high Z, or basically not connected anywhere at all. So for doing that in System Verilog, you can just simply assign it with Z. So the internal design of System Verilog understands Z as high impedance. So let's just create a module, basically a set of tri-state buffers. So for the input, we have A, and these one again have 4 bits, right? So A is 4 bit. We have this enable signal, which is 1 single bit, and then we have the output, which is again 4 bits. But one thing that is different now is that instead of logic, we are using this keyword try. So that tells System Verilog that the type of this y is not only logic, it's not only 0 or 1. It has a third state too, or it is a tri-state output. Right? So this is very important. So if you just specify as logic, then you cannot assign it 0. You're gonna get an error. But since y here is a tri-state output, you need to specify the type as try here. And then you just say assign y equals enable question mark a colon 4 single quote bz. So what does it mean? It means that if the enable signal is 1, y is going to be a. However, if enable signal is 0, y is going to be z, 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 z. So remember, the input and output are all having 4 bits, right? So this is in fact 4 tri-state buffers side by side, which they all get the same, you would say, enable signal. So this is enable, and then we have the output y to look like y3, y2, y1, and y0, and then the inputs are a3, a2, a1, and a0. So as you can see, by using the ternary operator and defining this output as a tri-state output, you can either assign it a variable or a logic variable, because A is logic, or you can assign it high Z. So the last thing that I want to talk about in this video is with regard to delays. Because if you remember from the previous video, when we did the simulation, we just said we have all the combinations of the inputs over time, and then for each one we calculate what the output is. But when we talk about time, it is appropriate to talk about the delays too, because if you remember from a previous lecture, when we introduce delays, then we may end up having glitches, right? So let's just see how this thing can work for a simple module. So in this module, which I appropriately named it example, we have input, logic, A, B, and C. So we have three input, A, B, C, and the output logic is Y. Inside, I have defined several internal variables. One is AB, the other one BB, CB, and then N1, N2, and N3. So the first line of assignment says, let's just ignore this for now. We have AB, BB, and CB all inside these curly braces, and this equals tilde of curly braces A, B, C. So this tells system Verilog that AB is tilde A, BB is tilde B, and CB is tilde C. So instead of writing this 3 times, we can just simply do it like that, and system Verilog understands it. But this #1 tells that this process is done with 1 unit of delay, right? So this unit of delay can be anything, right? It can be 1 picosecond or 1 nanosecond, but the important is that it is 1 unit of delay. So as soon as you provide inputs A, B, and C, it takes 1 unit of delay for the values of AB, BB, and CB to be calculated. Now let's just go to the next line. The next line we have N1, which is AB and BB and CB. So it is basically the result of ANDing the complements of A, B, and C, because AB was basically, if I want to write it, AB, the variable, don't confuse this with ANDing A and B. It's like a single name, right? It's a single name. So this is basically A bar. This one is B bar and this one is C bar. So N1 is actually A bar, B bar, and C bar. And to calculate this, whenever the inputs are available, it takes 2 units of delay for this calculation. For N2, this is equal to A, B bar, C bar. And for N3, this is equal to A, B bar, C. So as you can see, these three input AND gates each take 2 units of delay to calculate their output. And then finally, the final function Y, which is the OR of N1, N2, and N3, it takes 4 units of delay. So Y is basically N1 or N2 or N3. So now let's see what we can have when we simulate this function. So at the beginning we provide inputs A, B, and C, and then after 1 unit of delay, the value for AB, BB, and CB are created. So this is pretty straightforward. But now when we get to N1, N2, and N3, you see that the results are calculated at different times. You see N1 has its value at time 3, while N2 and N3 have their values at time 2. So when we have A, B, C as 0, so let me just quickly write the function that we want to calculate. So it is A bar, B bar, C bar plus A, B bar, C bar plus A, B bar, C. So as we said, each one of these to be calculated takes 2 units of delay. So after the complements are being calculated with 1 unit of delay, you need to have 2 units of delay for these 3 terms each to be calculated. But as I said, N1 takes longer to be calculated than N2 and N3. Why do you think is causing this? What do you think is causing this? So the answer to that is dependent on the way that you interpreted one sentence that I said in the previous video. Is that when you are writing system Verilog, you should think of the hardware that is being implemented. So let's just quickly draw the hardware without any simplification so you know what I mean. So for the first, second, and the third AND gate, we have some inputs. So for the first one, we have A that goes through a NOT gate and will be considered as input. For B, we have another NOT gate, and for C, we have another NOT gate. And this calculates the first term for us. For the second AND gate, we have A, we have B NOT, and we have C NOT. And finally, for the third AND gate, we have A, we have B NOT, and we have C. And then finally, the final result is ORing these values to create the final function y. So we know that each one of these NOT gates has 1 unit of delay. Each one of these AND gate has 2 units of delay, and this one has 4 units of delay. But when you execute this function, or when you synthesize this function, it is not going through these lines one by one. So it doesn't execute them sequentially. What happens is that this circuit is being fully built, right? So all of these functions, the AND gates, the NOT gates, and the OR gate are going to be there, present. So as soon as you change the value for A, B, and C, they perform all of their functions, right? So for the first AND gate, you have to calculate A bar, B bar, and C bar, right? Because at the beginning, all of these are 0. So what you have is that for the first AND gate, A bar, B bar, and C bar are going to be calculated, which means that all A, B, and C need to go through this delay for their value to be calculated as input of this AND gate. And when A, B, and C are all 0, these 3 are going to be 1, and the output is going to be 1. But you don't have to do the same for N2 and N3, because A is 0, B is 0, which means that this one is 1, C is 0, which means that this one is 1. So you actually calculate A being ANDed with A, which is 0, being ANDed with 1 and 1, which the output is 0, right? But as you can see, A doesn't have to go through this inverter anymore for creating the second term. And that's why the result of this AND gate appears sooner. The same is true for this one too. A and C don't have to go through this inverter. They are directly connected to this AND gate. And you remember, 0 was the null element of the AND gate. So if any of the inputs is 0, the output is going to be 0 no matter what. Right? So that's why we have this different delay for the result of N1, N2, and N3. So we can go step by step. First, after one unit of delay, we calculate A bar, B bar, and C bar. Then the next thing that would be executed is going to be N2 and N3, because we have A without the need to go through any inverter is present. For this one we also have C2, right? So the values for N2 and N3 are going to be calculated sooner. For N1, since all of them had to go through this inversion or like complement process and then go through the delay of the AND gate 2, it takes longer, right? And then finally N4, Y, which has 4 units of delay, its value is finalized after all N1, N2, and N3 are finalized, right? So since N1 is finalized at last, 4 units of delay after this, you have the value for Y. So this is something that you should always consider, that as long as all the elements are ideal, you don't have to worry about that. But as soon as you introduce physical limitations, especially like delays, then you may end up in situations that your outputs are not exactly behaving the same way that you want. So this is something that you should always keep in mind.